Good morning, everybody. It's a pleasure to start the morning session with Ignacio Vergara, who is talking about property T for uniformly bounded representations.
Let me start by thanking the organizers for inviting me. My first time in Cambridge has been great conference. So today I want to talk to you about a strengthening of property T, or more precisely a family of strengthenings of property T, using uniformly bounded representations where we fix a bound for these representations. And so I'm going to talk about that and I'm going to try to convince you that that this is something interesting. Okay, so let me start with the main setting. So the setting is the following. So I'm going to have a G will be a locally compact group mainly because some of the interesting examples will be Lie group. So I do this at this level, and H will be a Hilbert space. And I'm going to look at representations. So we have already seen this in a few talks. From G to the bounded operators on H, which are uniformly bounded. And what I mean by this is that if I take the supremum over all the elements of the group of these norms, then this is finite. And I'm gonna call, maybe I'll use a color. I'm gonna call this number the norm or modulus of I. Okay, so I'm gonna continue here. Okay, so this is the class of representations that I'm going to be looking at, and of course, this number is 1 if and only if the representation is unitary. So yes, you can already guess what follows. But oh yeah, I'm just going to say I'm only going to be interested in representations that are continuous for the strong operator topology. So yeah, I'm not going to write it, but I'm only looking at those. When the group is locally compact, if it's discrete, it doesn't matter. And I'm going to make the following definition. So for C, a number bigger than 1 or equal to 1, I'm going to consider the class RC of G. This will be all the uniformly bounded representations such that this number is bounded above by C. Right, so consider this class of representations. I give this name RC. And of course, as I already said, so the remark is that R1 of G is exactly the class of unitary representations. Okay, so this is the class that I'm going to be looking at, and with this I'm going to define this stronger version of property T. Let me see if I want to say something else now. Which, yeah, you can guess the definition is the spectral gap condition. So the definition is that so I take a number, I fix a number C greater than or equal to 1, and I will say that G has property property TC, and I'm very glad that, so I'm putting the C outside of the parentheses so my notation is not conflicting with yours. So G has property TC if we have this spectral gap condition. So if for every representation in this class without invariant vectors, without non-trivial invariant vectors, so we can put the quantifiers in the order that we like. I'm going to say there exists epsilon and there exists a compact subset of G such that for every psi in my Hilbert space, so this is the Hilbert space associated to this representation here, the supremum of, sorry, this is Q, S in Q of this difference is bounded above, below by epsilon times the norm of psi. Right, so this is my definition, property TC. It's just extending the known notion. And of course, property T1 is property T. So remark. So property T1 is exactly property TC. I mean property T. And we can see directly from the definition that if C grows, this property becomes stronger. In principle, it becomes stronger. So if, let's say, C2 is bigger than C1, property TC2 implies property TC. TC1. Okay. So in principle, this becomes stronger. Yeah, that's all I want to say. Okay, so that's the definition, and this is just the first remarks. And I want to say a few words about Kashtan projections, mainly to connect this a little with strong property T. So at some point I thought about giving as a title not so strong property T, because it's stronger but not that strong. But okay. So Kashtan projections. So this was already mentioned in Cornelia's talk. I'm going to repeat a lot of things, but in this particular setting. So, so the first remark is that since these representations are uniformly bounded, every representation in this class can be extended to L1. So I have my group is locally compact, so I can endow it with a left hard measure, and I can consider the L1 space of it. And for every function in L1, and every representation in this class, I can extend the representation to this function. So I can define phi of f as the integral over g of fs phi s ds, where this is a bounded operator, and yeah, so this integral makes sense as a limit in the strong operator topology, and this is a bounded operator whose norm is bounded by the L1 norm of f times c. Okay, and so doing that, I can define something analogous to the group sister algebra. So I'm going to continue here. So I'm going to define A tilde C of G. This is PCS notation, that's why I use it. This is the completion of L1 for the norm, the supremum over all the representations. So this is the supremum of the norm of pi of f, where pi ranges over all representations in this class. So I have this and this Banach algebra for this norm, where the product is just the convolution on L1, and naturally from the definition, every representation extends to an algebra morphism from this algebra to the underlying Hilbert space. So, yes, so that's my definition. This is PCS definition. I'm gonna write it here, PCA. Maybe the notation is a little weird, but that's because PCA defines this in a much more general setting for representations of algebras, in which case one understands why the notation is like this, and then it just got inherited to the group case. Okay, and of course, so again, a remark, A1 tilde of G is nothing but the full group sister algebra of G. And so just like property T can be characterized in terms of Kashtan projections here, this property TC can be characterized by Kashtan projections here. So I'm going to write all that in detail. Let me see if I want to say something else before. Okay. Okay, so I'm going to state this theorem. So this is essentially by Drutu and Novak from when? From 2015. So they have a very general result, which I'm going to state just in my very particular case. And so it says the following: so let G a locally compact group as before, and C bigger than 1. Then the following are equivalent. So first, G has property TC. G has TC. And the second one is the existence of the Kashtan projection. So there exists an element of this algebra which is an idempotent, so such that P squared equals P, and such that when we apply any representation in here, we get a projection onto the invariant vectors. So for every pi in this class RC of G, pi of P is a projection. It's not necessarily an orthogonal projection. It's a projection onto the subspace of invariant vectors, of pi invariant vectors. Okay, that's. So there is, as I said, the result is far more general. This is in my very particular case, how this can be expressed. And so I wanted to mention this because, as Cornelia said in her talk, this is the point of view that Lafort took for the definition of strong property T. And so for strong property T, instead of considering uniformly bounded representations as here, one considers representations with a certain control of the growth. And so in particular, these representations are in that class, so strong property T is stronger than any of these properties here. So that's the remark that I wanted to make. I'm going to use blue. So strong, let's say Lafort, strong T, this implies TC for any C, and this implies T. And yeah, maybe this is not a good color, but okay. We're gonna see that the equivalent, those are not equivalents if we put the quantifiers in the right order.
What is the example of representation of like with uniformly bounded but not representation of a group on a Hilbert space which is uniformly bounded but not unitary?
Yeah, so that was a big problem, and yeah, it's a difficult question, and it took a lot of work.
But then how do you know you're not proving zero? I mean,
So if your group has a free subgroup, you know that it has uniformly bounded representations that are not.
what is example?
So I can, I cannot give you like directly what it is, but you have to go
Okay, but
through.
we know they exist.
Sorry?
We know they exist.
Yes.
But I really want to think about an example.
But isn't it just a perturbation of a unitary one by some kind of bounded co-cycle? It's just by exuding one is a pain. No, I guess on a figure you can do it, right?
But I think it should be remarked that, I mean, regarding the fixed point property questions, just the existence of uniformly bounded representation is something quite classical that appears in the classification of reducible representation of semi-simple groups. Maybe you want to make this.
Okay.
We're happy to know that it exists on a free group. I'm sure it's a very nice formula that we'd love to write out another problem.
Okay, and I just want to mention that this property can also be characterized in terms of the weak star continuity of a certain invariant mean, but I don't have time to talk about that. I'm just going to mention it. But that was my main motivation when I started working on this. I wanted to say that. Okay, so the third part is we can associate a constant to these, a number to these properties. So as I said, these properties become stronger as C grows, or in principle they become stronger. So we can look at the moment of at which the group stops having this property in a certain sense. So this is what I call the constant CUB. I couldn't think of a better name. So I'm going to define CUB of G for every locally compact group. I define this as the infimum of all C such that G does not have TC. Right, and I'm using the convention here that the infimum of the empty set is plus infinity. So if the group has property TC for every C, then I'm gonna say that this number is plus infinity. And if it doesn't have property T, this number is 1. So this is something that belongs to 1 infinity included. It quantifies how strong this property is. Okay, so that's the definition of this constant, and it has some nice properties.
Sorry, can I ask, so reading the definition again, it seems to be quantifying for implies after the existing.
Yeah, I mean you
say so you swap the two quantifiers. Right?
Yes, they are both equivalent.
Okay, because you want to build some. Okay. Yeah. You make it more tricky for us.
Yes, I mean, yeah. I guess that this one is the original definition, and the other one is you prove it as a theorem, right? That you can take epsilon uniformly. Okay, so this has some nice properties. So first, so if this constant is bigger than 1, then by definition the group has property T, but actually that is an equivalence. So G has T if and only if this constant is bigger than 1. And this was already mentioned by Cornelia, but in a different setting. This is essentially a result by Fisher and Margulis. Yeah, where they show that a Kashtan group has the fixed point property for 1 plus epsilon Lipschitz actions on Hilbert spaces for epsilon sufficiently small. And there is also a result by Michael in a more general setting, so I'm going to mention that using the Kashtan projections. So, but the original, I mean, Fisher-Margulis is enough for this. What else? So this constant behaves well with respect to products. So if you take the constant of a product, this is the minimum of the constant of each group. And this is actually a particular case of a more general property for quotients or extensions, if you want. So if if we have H a subgroup, closed normal subgroup, then this constant for G can be bounded above by the constant of the quotient and below by the minimum of those. So min. And this is, yeah, this is just repeating the argument for property T, that property T passes to quotients and that it is stable under extensions. If you repeat that argument for this property TC, you can deduce these inequalities. And this one, of course, is a particular case of this one because a product is an extension. And the last one that I wanted to mention is that this, as classical property T, it behaves well with respect to lattices. So if we have gamma a lattice, then they have the same constant. Okay, so those are some nice properties, but they are just really just extensions of what we know for property T. There is one more property that I want to mention, but I'm going to state it as a theorem. So, yeah. This is in 23, I guess. It only appeared in the second version of the paper. This property is stable under von Neumann equivalence. So I'm going to write that down and I'm going to explain what that means. So let gamma and lambda be countable groups, countable discrete groups, such that gamma is von Neumann equivalent to lambda, then they have the same constant.
They have the same von Neumann output?
No, I'm going to explain. So, this is von Neumann equivalence. And it's a notion that was introduced, let me write it, by Ishan, Peterson, that's an E, and Ruth in 2019, I think. And this is something that can be thought of as a non-commutative version of measure equivalence. So, what is measure equivalence? Two groups are measure equivalent if they have actions on a measure space, commuting actions on a measure space, such that each one of those actions has a fundamental domain. So a finite measure subset such that when I look at the orbit of this subset under the group action, I get a partition of my measure space. So if we have those properties, we say that the groups are measure equivalent, and this notion here is the non-commutative version of that. So let me write that down and explain. Okay, so measure equivalence. This means that there are actions of gamma and lambda on a measure space. So these are commuting and measure preserving, and such that each action has a fundamental domain. Each action has a fundamental domain, right? So as I said, a finite measure subset, such that when I look at the orbit of this subset, it gives me a partition on the measure space. And von Neumann equivalence is the same thing, but we replace the measure space by a von Neumann algebra with a trace, and we replace the fundamental domain by a projection. So von Neumann equivalent, this is the same thing, but with a von Neumann algebra and not with a trace.
Semi-finite.
Sorry?
Semi-finite?
Yes, probably, yes. And in this case, the fundamental domain is a projection. So, since
Finite trace.
a finite trace, yeah. So, since commutative von Neumann algebras are exactly the L infinity L infinity spaces, and projections on those spaces are exactly the indicator functions of measurable subsets. This property here implies this one, because we can pass to the L infinity space, and we get this notion. The other direction, as far as I know, is open. So I think we still don't know whether these properties are equivalent. But
In the first definition, there's a relationship between the fundamental domain and the action, but in the second definition, there's no relationship. It doesn't seem to be a relationship between the projection and there's something not symmetrical.
yeah, so I was a little sloppy here. I didn't write, but the projection. Yeah, so I didn't mention it. So here we look at the orbit of the fundamental domain, and it gives me a partition of the space. Here we look at the orbit of the projection, so that we have trace-preserving actions on the von Neumann algebra, and we look at the orbit of the projection, and that gives me the sum of all that gives me the identity of my von Neumann algebra.
For each of the action. For each action.
Yeah, each action has its own fundamental domain. Yeah. Yeah. Sorry. Yeah. I skipped some important details.
The orbit of the projection, they all commute with each other.
Sorry?
The orbit of this projection, they all commute with each other. If I apply the action to the projection.
Both actions commute.
No, with the different projections when I apply.
Yes.
Yes, they must.
Also, without projections, they commute because the product is zero in both directions.
So they will be destroyed.
Yeah. Yeah. So we really get the same picture that we're filling the whole space, but in this case we're filling the identity of the algebra. Okay, so we have that. As far as I know, we don't know if this is an equivalence, but this comes with some nice features. So I wanted to focus on the corollary, which is now what you mentioned. So the corollary of this is that when they introduced this property in the same paper, they proved a lot of things about this property. One of those is that if two groups have the same von Neumann algebra, then they are von Neumann equivalent. So the corollary is that if two groups have the same von Neumann algebra, then they have the same constant. The corollary is that if the von Neumann algebra of gamma is isomorphic to the von Neumann algebra of lambda, then CUB of gamma is CUB of lambda. And, well, of course, if they are measure equivalent, we have the same conclusion because of that. But I wanted to mention this corollary now. I don't know if this is ever going to be used to distinguish between von Neumann algebras, but still I think it's nice to know that there is one more invariant at our disposal. Yeah, I wanted to mention that. Let me see if I want to say something else. No, that's all. Okay, so now let's go to...
Can you say a word about the proof? I mean, because this is not a star action. So can you prove your theory?
Proof of this?
Yes.
Yeah, so it's a little convoluted. I think there has to be a more direct proof using simply inductions of representations. I mean, in their paper, they prove that property T is stable under this notion, and they induce representations in a similar way. I'm not going to say similar way, but in the non-commutative way, similar to the classical induction of representations, and then they obtain their result. What I did was pass through, go through a different notion of objects. I used Fourier multipliers of these groups, and another class of functions that was introduced by Pizier in order to study the Dixmuir problem, where you have decompositions as products on Hilbert spaces. Well, it's a complicated definition, but I used that kind of functions and a result by Batzeren that says that some approximation properties related to those particular multipliers are stable under this notion. So I used that plus some combinations with the Kashtan projection, and then I am able to obtain this. But yeah, I would need to define a lot of things to enter in the details. So now, I want to mention examples now that I've done this. So this should be 4. Yeah, so as I said, the main examples come from Lie groups, and I'm gonna state immediately this theorem. This is by Dooley in 2002. Which I'm not going to state in a very precise way, just in a way that I need. And it says the following. I'm going to consider rank 1 Lie groups, as was already mentioned. there are essentially four classes or four local isomorphism classes of simple rank 1 Lie groups. We have two of those where the groups have the high group property, so I'm not going to talk about those because they are not relevant in this setting. And the other two, so the isometry group of the hyperbolic space over the quaternions and the similar thing for the octonions, those have property T, so those are relevant in this setting. And this theorem by Julie says the following, so let G be either SPN1 right? So this is the automorphism group of the n-dimensional hyperbolic space over the quaternions, or the exceptional Lie group F4 minus 20. This is a similar thing, but with the octonions. So the results says more things, but I'm just going to write that there exists a sequence of representations such that this representation converges in some sense. I'm not going to say more about that. In some sense to the trivial representation. And the limit of this thing, so yeah, I already erased it, but this is the supremum of over all the elements of the groups, of the norms. This converges to a number, which is a very important number, so it has a name. It's the Cowling high group constant of the group. If you don't know about weak amenability, it doesn't matter, but this has a name and it's an important thing. And this is 2n minus 1 if G is SPN1, and it's 21 if G is F4 minus 20. Right, so this is the result by Julie. Disclaimer, I don't really understand this proof. So I tried to read the paper, it was too hard for me. So I'm just going to use this as a black box. Okay, so, but I'm interested in the consequences of this. Oh, okay. Okay, so the consequences of this is that this constant CUB of G for those groups, this is bounded below by 1. This is just the fact that this group have property T, so this has been known for a long time. This is constant. In 71, I think. But with this, we can see that this is bounded above by this Cowling high group constant, which is, yeah, related to weak amenability. And yeah, just a few words. So Cowling high group, when they proved weak amenability of these groups and they computed these numbers, they used uniformly bounded representations, but the representations were uniformly bounded, but their norm exploded when approaching the trivial representation. So Julie's contribution was saying that we can do this, but in a uniformly bounded way. And yeah, this constant, as I said, is important. It's also an invariant at the von Neumann algebra level. But yeah, I don't have time to say more about that. And one corollary that we get from this is that these groups have proper uniformly Lipschitz actions for C big enough. So for G as above, and C bigger than this number here, G has a proper C Lipschitz action on a Hilbert space.
Do you get proper right away or just bounded orbit?
Sorry?
Do you get proper immediately or it's just...
Yeah, so that's the magic of simple Lie groups. So in general, from the fact that this is finite, we can conclude that the group has an action, Lipschitz action with unbounded orbits. But for simple Lie groups, there is a dichotomy that they either have proper, the actions are either proper or they have bounded orbits. So thanks to the fact that these are simple Lie groups, we can get that directly. And yeah, so I have just a few minutes, so I'm not gonna write the next. Oh yeah, I have to mention Nishikawa. He was already mentioned in a few talks, but yeah. So as it has already been said, there are similar results by Nishikawa. But yeah, so he does all the work. I mean, he doesn't use this result by Dooley. He constructs the representation and the ecocycle and the action. Yeah, so this is from 2020, I think. And yeah, so I want to mention that. Okay, so let me just quickly say that again we can use random groups in this setting. It was already mentioned by Cornelia, and for random groups we can use a result by two of the organizers, by Michael and team, where they studied very general things, so fixed point properties for uniformly curved Banach spaces. And their very general results can be adapted to this more particular setting. And if one does all the translations, one can see that for every C bigger than 1, I'm just going to write something very vague. Hyperbolic groups let's say gamma with CUB bigger than C, I'm going to write R abundant. Right, so this was dealing with upper bounds for these constants. Sorry, this is dealing with lower bounds with these constants, and there are hyperbolic groups for which, I mean, for every C we can find hyperbolic groups with constant bigger than C, and not only that, we can find a lot of them. Okay, and this can be made very precise with the language of random groups, and I'm not going to do that. And let me just, so recall this small diagram. So we had strong T that implies TC, and this is for every C bigger than 1. which implies T. And we know that this here doesn't hold by looking at SPN1 if we choose the right C. And we see that this one doesn't hold in a very strong way looking at hyperbolic groups. Because one of the many things that Lafort proved when he introduced strong property T is that hyperbolic groups don't satisfy strong property T. So for every C we have a group that satisfies this, but not this. And yeah, so I wanted to mention this, and I'm gonna finish by a question related to what has already been mentioned, Shalom's conjecture. This is in the same flavor, but not exactly the same thing. Does every hyperbolic group gamma satisfy CUB gamma finite? So this only tells us that the constant is big enough, but it could be infinite, right? So this is the question. And with that question, I finish my talk. Thank you.
Thanks a lot. We have time for 1 or 2, 3 questions. Is this what Cornelia called a weak Shalom conjecture?
It would imply, yeah, it would imply the weak Shalom conjecture, yes.
The weak Shalom conjecture is that there is such a representation with an unbounded cocycle.
Yes.
And well, if you don't have spectral gap, you always have unbounded cocycles. That's the connection.
Okay, let's thank Ignacio again.